Good afternoon, everyone, and welcome to another webinar in the Al-Khwarizmi Applied Mathematics webinar series. Today, we are truly honored to have Professor Malgorzata Peszynska as our speaker today. Professor Peszynska is a distinguished professor at Oregon State University in Corvallis, USA. She received her PhD in 1992 from University of Augsburg in Germany. Her research interests are in applied and computational modeling of real-life phenomena such as flow, transport, and coupled processes. She is an author and co-author of more than 100 peer-reviewed publications, scientific research, and articles. She has received numerous awards in recognition of her substantial contributions in the field of mathematics, such as OSU University Distinguished Professor in 2024, Siam Women's History Month in 2023, Joel Davis Faculty Scholar in 2022, and more. Today, she will talk about mathematical modeling, analysis, and simulation of heat conduction in frozen soil in the Arctic. We are looking forward to this great talk. And Professor Peszynska, the floor is yours. And go ahead and please get started.
Thank you very much for the invitation, and thank you everybody for joining us today. My special thanks go to Dr. Ashar Al-Hamali, who is a dear colleague, and I really appreciate the invitation and the opportunity to speak at the Al-Khwarizmi seminar today. What I will be talking about is about the Arctic, and I don't know how many of you have traveled to the Arctic, but I have. Just this last year. I went to Alaska, and the things that I experienced myself are even giving me even more motivation to study what I will be talking about today. So first, I would like to thank many of my colleagues and collaborators and co-authors and students, some of whom you see here, right? She's one of your colleagues right here, but I would like also to acknowledge most recent collaborators to this work that include Pravini Mathangadira, Madison Phelps, Forrest Felsch, Corbin Savage, Nicholas Slug, and Noah Unger-Schultz. And my earlier work on pore scale has been with Dr. Anna Trojkowska from University of Warsaw that unfortunately passed away 6 years ago now. Okay, first of all, I want to give you some motivation for this work. So you see here the picture of essentially the North Pole right here with various countries in the Arctic area of the Earth with some of the regions marked in deep blue and lighter color of blue that mark the regions where there are soils with permafrost. So what is permafrost? Permafrost is the ground that is frozen for 1 or 2 years. And there's less and less of the permafrost, and there will be likely consequences for the global climate if this trend doesn't change. Of course, who knows how things are going to go. Maybe some of you are probably more junior than I am, but maybe in 20 years, you will see how much of the ice and how much of the permafrost is still there. Okay. So I will be talking to you today about a variety of modeling concepts across the different scales. So the traditional scale at which people model flow, transport, energy is the macro scale, the field or reservoir scale. So for example, I was, by the way, involved for many, many years in modeling oil and gas reservoir simulation. And when I was at the University of Texas at Austin, we had projects with Saudi Aramco. So that's when we worked at the field or reservoir scale. And this is the scale. You see some people here of roughly, I don't know, meter kilometer scale. In order to model phenomena of that scale, people take laboratory measurements. They core samples and they take some measurements. And for the oil and reservoir industry, it was known that we cannot really always use the measurements from the laboratory and use them in models at the reservoir scale. So people decided the best way is to do something called upscaling. So you see here the arrow that points up. When I came to Oregon State University about 20 years ago, we started working on a different connection between the scales, between the pore scale and the laboratory scale. So here you see pictures that people take. They take tomography pictures, just like micro CT of your body. People take pictures of the media, and then we try to model fluid flow, biofilm growth, just like Dr. Al-Hamali has been working on and did amazing work, and then try to upscale this to laboratory scale. And the idea is that one time we might be able also to upscale this to the reservoir scale. So this is an overview. So with spatial scale, of course, you have to also look at the time scales, what's happening at the pore scale at such a small, tiny scale of nanometers or millimeters. It happens maybe at the scale of seconds or of hours, whereas things that happen at laboratory or field scale take maybe days or years. So one has to recognize these different scales when you try to model very complex phenomena. So today I will focus again on permafrost. So the reason why we want to focus on permafrost is that it's changing, as I mentioned, and you can see here what's happening with the infrastructure in the different parts of the Arctic. So buildings collapse, railroad collapses, because when the soil thaws, the ice that was holding the soil together all of a sudden does not provide that structure anymore, and the ground subsides in some pretty much unpredictable way, and there's a lot of damage to the infrastructure. Also, the coastline is eroding. You see here the image of how soil lost its integrity and essentially disintegrated, and lots of coastline in the Arctic is receding because of the thawing of permafrost. So we don't say melting, we say thawing. So to model such phenomena, you really should be looking at coupled systems. Today, I will be focusing on the energy equation, so what we call TP, so thermal with phase change. But you also could see my work with collaborators also on other processes, including the flow, so hydrological processes, and deformation. So I think there are a lot of efforts in your country, in Saudi Aramco, where people are studying flow and deformation of oil and gas reservoirs. Here, what I'm talking about also, these phenomena are important, but maybe at a different, in a different context. So I'll be focusing on the energy equation, so heat equation. Okay, so we go now to some more overview. So what does permafrost look like? At the landscape scale, you see here some mountains with ice and glaciers. You see some water, surface water. You see the permafrost region on the left with a lot of ice, permanent ice wedges embedded in them. And you see a lot of phenomena that are coupled to this problem. You also see how temperature is changing. So now you're looking down with gravity, you see how the temperature in red here is changing. It's changing primarily in the so-called active layer. So that active layer here on the picture is the layer of soil where the temperature is changing. It's pretty much doesn't change below, where the ground is permanently frozen. But it's important to know how deep that active layer is, because the depth of the active layer determines how many other phenomena are happening, such as methane escaping from underground, such as the stabilization of the top structure. So as I mentioned, I will be talking today about the connection between the two scales, the pore scale, where you're looking at the individual grains of rock, and the Darcy scale, where we write traditional partial differential equations to model the phenomena. And our results led us to those kinds of simulations, where you're simulating how the depth of the active layer has changed if there is a temperature on the surface change. Now, with climate warming, it's just going a little bit up every year, and the depth is dramatically changing. You see here change in centimeters, but over many years, it's going to be a dramatic change. All right, so going to the heat equation. So some mathematics finally. We will consider heat equation just in a standard setting, an initial boundary value problem described here in this abstract Hilbert space setting as evolution of the temperature U with some heat conduction modeled by the operator A. So in this abstract setting, we also have to assume an initial condition. We have this operator, which will be the diffusion operator, which is linear from the domain of the operator to the space H. So typically H would be maybe space such as L2 of some spatial domain omega. And then the domain would be, for those that work in Sobolev spaces, you would be choosing for the domain to be, in particular, H01 Sobolev space intersected with H2. All right, so for a simple diffusion operator, it is known that A is monotone or accretive, if you like. And then it is also maximum accretive, which means in particular that the identity plus A is onto H. And if the domain, as such as that the one I described, is dense in H, then one can prove well-posedness of the problem, so that there is a solution C1, that's what the equation is asking us for, from time to the space H of that problem. So this is a standard setting. Now, as an example of this standard of the very abstract evolution framework, we can consider specifically the heat equation written here. So I don't show any coefficients here, but this is just the simplest example. You start with some boundary conditions, and here I assume that the boundary conditions are 0. And the minus Laplacian, along with the realization of the boundary conditions, together give us that operator A. And we assume some initial conditions. And let's say I have an example here on a region that I called Memphis, but that's sort of is a cartoon of the University of Memphis that I visited last year, of their emblem. So you can think of solving heat equation on such an emblem with coefficients of heat conduction and of heat capacity varying, but only confined to this domain. So you see here on the left a cartoon of the initial conditions. So we start with pretty much constant conditions here. And then you have some high proportions of heat somewhere else. But we know that after you let the time going, so this is the initial condition, the solution will be subject to infinitely fast smoothing. So you see here some of those high values eventually very quickly will dissipate. And eventually, as time goes forward, the solution is going to have very, eventually the stationary solution will be constant. So this is the property of the heat equation, infinite smoothing property. All right. Okay, so this was the theoretical example. Now we go to some more complex modeling concepts. So already we described the simple situation of the heat equation, which is built here, formula here from conservation of energy, then constitutive equations that tells us how the energy or enthalpy density depends on the temperature. So there is some portion that depends on heat capacity and temperature, in the simplest case linearly, or C is constant. Plus you have to add the latent heat of the phase change. So here I have a term that has the latent heat, the amount that's needed to melt some solid phase so that it will become liquid, times the phase fraction. And we combine it with the Fourier's law for heat conduction. All right, so we have this model. Once you put them all together, you get the heat equation that I just talked about. In here, in the simplest example, there's no melting, so you're only looking at one phase. So latent heat is 0 because you don't need to consider that. Then you can have heterogeneous heat coefficients and heat capacity coefficients. This model still exhibits the infinite speed of propagation property, and the regularity of the solution depends on how nice or nasty the coefficients C and K are. All right, then we look at the heat equation with phase change, which is something we, of course, need when permafrost is melting. So for that, we built a model that involves that latent heat. And the new, very important quantity is this proportion of water, of liquid fraction, liquid and ice fraction. So this is very interesting because this quantity, as you will see, is actually a multi-valued operator. And so we modeled this heat propagation with phase change using the Heaviside graph for liquid phase change. So if you probably remember, Heaviside graph for negative temperature gives you 0, for positive gives you 1, and in between it's a multi-valued, it's the whole interval between 0 and 1. I'll give you examples in a minute. So this type of a model does not have classical solutions. So you have to solve it in the sense of distributions, and where somehow, one say magically, this term appears under the time derivative, but it is directly related to the so-called Stefan condition on the interface that tells us that the jump of the normal flux across the interface is not 0, but it's specifically prescribed depending on the latent heat and the speed of the free boundary. All right, so this problem has very irregular solutions. Now, when you start working on permafrost soils, you will see that the problem actually has smoother solutions because the equation changes a little bit, and this function for water fraction is actually piecewise smooth. So you will see these examples in a minute. You will still consider it in the sense of distribution. All right, so I have my next slide, which summarizes the difference between the regularity of the solutions to the linear heat equation as opposed to the nonlinear equation, the Stefan problem, where you only have liquid, water, and ice, and then the permafrost models. So you see here that the difference is I have just one variable, U. Here I have two variables, U and W. So U is temperature and W is the enthalpy. And I have to close the problem by imposing a connection between U and W. And this is done with this multi-valued graph, alpha of U. So instead of writing W is equal to alpha of U, which you would do for the heat equation, linear heat equation, we write W belongs to alpha of U. And below here, you have examples of what that alpha of U is like. So for the Stefan problem in blue, you see here this multi-valued graph of enthalpy. For the linear heat equation, it would be the green curve. So just a simple, not multi-valued, potentially heterogeneous curve. And then for the permafrost model, you see a little nicer function. Oops, sorry. A little nicer function that is continuous. There's no multi-valued property, but there's still some corner here of the function. So anyway, as a result, you have regularity that I described here with infinite smoothing property, but for the Stefan problem, you have much, much less. And for the permafrost model, we have just slightly better solutions, but not much more due to this corner. So you see here, we don't even have C1 in time. We only have L infinity in time going into L2. We have H1, but it's then going into the dual space of H01, which is H minus 1. So this problem has been very well studied. What we were interested in is studying this problem from the Poor scale to the Darcy scale. So again, now we are looking only at the Poor scale, where you have this multi-valued water fraction and the multi-valued enthalpy temperature graph, and then the Darcy scale, where you have a smoother water fraction in magenta here, and then you have a smoother, potentially multi-valued, but we have mostly worked with single valued smoother enthalpy temperature diagram. And so you write that model, and I repeated it for you again. It's written in temperature. This time I will be using theta because there's so many U's in the coupled systems that we switched to using temperature theta and enthalpy W. And definition of W is here. Again, we have the inclusion where W belongs to alpha of theta. There's the heat capacity term, and then there's the water fraction term with latent heat. And then the C term just averages the heat capacities of the different materials. Okay, so this is a comparison of the two models. Now, what do we do with it? And I have here a simple, maybe a couple of simple videos that show how these solutions behave numerically. So you see here the data that you just saw before, and here you will be looking at the simulation of the solutions. Can you see the movie, by the way? Dr. Wissam, can you tell me if you can see the Dr.
Yes.
Al-Hamali?
Yes.
Yeah,
Yes.
you can see. Yeah, very good. Thank you. So you see here temperature in red, and that temperature is continuous. And what we are modeling is that starting from initial condition which was constant, and raising the temperature on the left-hand side, we're modeling the melting of the ice going forward to the right-hand side. So going slowly, you see here the enthalpy in blue is discontinuous because we are supposed to have a discontinuous graph. And then water fraction is also changing dramatically, and we see the temperature is continuous. So this is typical behavior of the solutions to the so-called Stefan problem with only liquid, water, and ice. Okay, on the next slide, what you see is, however, what's happening in the soil. So you have ice and water, and you have sediment. So you have a lot of very complicated Poor scale view of the soil, which includes some frozen portions of the domain. These images were taken by X-ray, computed tomography, and we got them from literature. They motivate very well our work. Now, solution to this problem is extremely irregular. So there has been some work done on the regularity. Basically, you don't have much to go on. Of course, you have to work in the sense of distributions, but you don't have much to go on because there will be additional jumps across the material interfaces. And by material interfaces, I mean between sediment and the water domain. So for example, I have a quick simulation that shows additional free boundaries, additional discontinuities. You see how the solutions are really having a hard time, even though the temperature is continuous. You see here that enthalpy takes multiple jumps when you go across the interfaces. But that's at the pore scale. Now, once we start averaging and you go to the Darcy scale, all these relationships become much smoother. And that's how you will see here my simulation that illustrates that the solutions are very smooth, much smoother than they were before. So you're looking here at the comparison of water fraction and now temperature. Temperature is very nice, even across the front, and everything works much, much better. All right. So we were very interested in explaining what goes on when you switch from this scale, which is super irregular, to this scale where things get smoothed out. And we set out to explain things. But first, maybe let me mention very quickly that we have been using a very new numerical scheme, which was built from old schemes, but people have not used that scheme before. So we used a mixed finite element method, just like Dr. Al-Hamali pioneered the use of mixed finite element methods for very complicated nonlinear parabolic problems. We used a similar approach and approximated temperature and enthalpy here as piecewise constants. Here's an example of how that's done. Traditionally, this was done with piecewise linears, and even though it seems to be giving you more continuity of the variables, unfortunately, it also means that with the traditional approach, you have discontinuous fluxes, which is quite bad for heterogeneous materials. So in our approach, I will not be giving too many details on that, but in our approach, we decided to use the so-called P0, so piecewise constants, and the RT0, which is a really good space, robust space for modeling fluxes. All right. So I will not be showing you details of the numerical analysis of the solver, but we have some papers that that show the details. One important thing to mention is that we had to implement a really good nonlinear solver. And since we wanted that solver and the the energy model to be part of a very complex system, we were not really able to, we could not afford the solver to fail. So we took a long time to build a solver that would be robust. All right, so now some examples of convergence that probably will skip that, but we did a lot of diligence to study convergence. And we were able, also I showed you before one-dimensional examples, we were able to solve things in 2 dimensions with some very interesting cross-sections of the results. Now, one thing to mention here, so you see an ice wedge and the soil domain and maybe another heterogeneous domain. What you see here is the appropriate behavior of the water fraction, and depending on what you assume, whether that's ice or a different type of soil, we looked at the cross-section along this transect to show in detail how if things are changing. So we can do all of these solutions, and yeah, we were very pleased to see that. All right, so now going towards upscaling. I said that this will be an important part of my talk, and I will give you an overview of our results, not the details. So again, we are going from different spatial and temporal scales, and we are looking at going up. So we go from the pore scale to the Darcy scale. And I want to mention to you that, of course, upscaling is a subject with a very long history. I wrote here some sort of overview of what people have done in upscaling for over many years. And essentially, all the materials that we deal with are multi-scale. Coal is multi-scale. Concrete, reinforced concrete is multi-scale. You have fibers of steel uh, interspersed with concrete material. Mangrove forests in nature and multi-scale. You see here some vegetation with fluid going in between. Human body tissue is multi-scale. So you see here a picture of skin. And wood is multi-scale. So you see here laminated wood. This is, by the way, a picture from Oregon State University where they are studying different ways of engineering laminated wood. So typical efforts, as I mentioned, go from the lower scale up to find the upscaled coefficients. All right, so we'll work on that now. So as an example, first, we study a stationary heat equation, a boundary value problem, where you have coefficient K of this equation that changes periodically. So I'm showing here a domain from 0 to 1, and the coefficient jumps. The green dots show how the coefficient jumps. It jumps by a factor of 10 to the 3. All right, so the solution, the true solution, temperature, appropriately, has, it's continuous, but it has jumps in the gradient. All right, but it also responds to the external boundary conditions. So it goes from high to low, varying fast, but there is a certain global trend. So very frequently, we're just interested in that global trend. So rather than solving the problem at the fine scale, we try to find the effective solution, which is a limit as that scale factor goes to 0. So if you were looking at the same equation, but with a lot more of those changes of the coefficients, the solution would essentially resemble the black curve. That would be the effective solution. So you try to find effective coefficients that would give you the effective operator. And yeah, so the key is to find the effective coefficients. Okay, always good. In 2 dimensions, to find these effective coefficients, you have to solve an auxiliary problem. So there is an additional partial differential equation that you solve assuming periodicity. You solve for that auxiliary equation chi, and then you calculate the effective coefficient by averaging the solutions a little bit. So I have here 2 examples of what it would take to solve such an effective problem for coefficients. All right. Here's a 2-dimensional example. This is the emblem of Oregon State University this time with beaver picture. So you can imagine someone building a cake with a lot of those layers of white chocolate with some dark chocolate and some other colors representing different materials. So when you solve heat equation on it, you will find the temperature has this kind of a profile, or from the side like that. And you might be, again, interested in the global trends of the temperature. So here I'm showing a cross section along this transect of the temperature. So yeah, so we know how to do that. The difficulty going now from Poor scale to the Darcy scale is how to do it at the Poor scale. So at the Poor scale, we can also upscale flow, and we have done this for a long time. So I'm showing here very quickly just our results on upscaling flow models from Navier-Stokes to the Darcy flow. So you're looking at the stationary Navier-Stokes model, and when you upscale, you would replace this equation by the Darcy equation with some global trend. And we have done this for a long time, as I said. We can work both to discover this trend in some synthetic geometries, in some tomography data. Anyway, we've done this for a long time. But I wanted to talk to you about the thermal problems and how to upscale from the Poor scale to the Darcy scale. So there we go. We take the heterogeneous coefficients, conductivities, and the material properties of those alpha graphs. We take images, we upscale them, and then we compare with the effective data that practitioners have been using for modeling. How do we do that? I mentioned there are a lot of challenges. right? A lot of challenges, functionals are multi-valued. It's difficult to think of how you can upscale multi-valued coefficients to get the effective properties. Well, we found some theory written by Augusto Vicentin in 2007 that helped us understand how things should be done. So here are cartoons how to do it. Instead of starting with those multi-valued operators, as you see here on the lower left graph, we start with their integrals, or we say primitives. So these are convex functionals. We take the material properties of these convex functionals, we average these, and we get this red curve as the average curve. And then we take a subdifferential of these to get the solution. All right, so then the theory for that is provided in the paper by Vicentin, but we were successful in getting the solutions, and we have a paper on that. Additional difficulties from upscaling the heat conductivities, and one difficulty here is that the geometry of the region changes in time. You see here I'm showing a simulation of thawing. And so as you see, the distribution of the ice and liquid changes. So the coefficients also change. That's a challenge. All right. So now the big question was, are we done? Unfortunately, as an applied mathematician, I felt, okay, we're done. But, or maybe as an analyst, I thought we were done. But as an applied mathematician who wanted to simulate something real, we were not done. On the right-hand side, you see here realistic red curve that gives us this effective graph. But the one that came from upscaling was not like that at all. It was blue. So it had a jump. But we said that for permafrost soils, the practitioners noticed no jump. So why? It's because we did not include microphysics in it. So then we took some time to go back away from all that theory that was discovered by Vicentin, and to find a way to match. On the right-hand side, you see the successful effort to find a way to include several microphysics phenomena, including the freezing temperature that is different in different pores. And as a result, you see a successful match of the effective graph alpha compared to the practical permafrost models. All right, so that was successful. We also were able to upscale the conductivities, but I will not spend a lot of time doing it. I just want to say that we were very close to what the practitioners use, and our upscaling efforts show that you can go from microscale to pore scale with different geometries and find upscale properties and explain why they are the way practitioners measure in the laboratory from the pore scale up. That it's very nice to have mathematics and mathematics theory that helps us to identify useful models and explain the models at the Darcy scale. All right, so then we simulated. And you see here, very good agreement of the pore scale model, very good agreement with the models that were used by practitioners. So for temperature, you see almost perfect agreement with some difference.
What you said?
This is not our.
Not her.
Sorry, I heard some, maybe there was a question. And then you see the agreement of enthalpy. Of course, enthalpy would jump at the pore scale. So this is not a problem that you have a jump. We expect to have a jump. If we didn't, it would be we would be cheating. But the average values agree very well. Okay, so I'm almost finished. So that I can leave some time for questions. I want to mention that there's a lot more work that we are doing right now. I mentioned that this September, I took a trip to Alaska and we went to hike on glaciers. And you see a picture here, first of a glacier over a lake. And so you see a lot of body of frozen water. So that's glacier, and of lake. This is at the scale of 100 meters. And you see, we were there at temperatures above freezing, yet there's no equilibrium between liquid and ice at that temperature. Also, it's a lower scale, 1 meter scale. When you come closer, you see ice and water coexisting at temperatures above freezing. Not everything is melted. And here you see my foot. That's my foot and my finger showing ice and water coexisting at the temperature above zero. So there is lack of equilibrium. And we are having some projects where we are simulating, let me go down here, hysteresis between the temperature and water content. So not only do we have a multi-valued graph, but we also have hysteresis. As the temperature is warming, you have a different curve. When you go back and you freeze, you go along a different graph. So that's very important to model. And I want to finish by thanking you very much for listening to me today. And here are a couple of references to our recent work on the subject. So again, thank you very much for your
Thank you so
attention.
much. Thank you so much for this great talk. So we have maybe 3 minutes for questions. Are there any questions? Okay, so maybe I have one. So in slide maybe 9.
Okay.
So I think it's 9, yeah.
Mm-hmm.
Yeah, so the problem too, I think, is it equivalent to variational inequality because we have this inclusion?
That's a very good question. If you consider the so-called one-phase Stefan problem, it could be considered a variational inequality, because then people then assume that the temperature in the liquid is constant and is equal to 0. And so then you're solving and you're capping the temperature to be on a 0. But in the two-phase Stefan problem, you have this Heaviside graph. Let me show in here. So it's not quite the same as variation inequality, but yes, there is a free boundary. So I know you're an expert on variation inequality. So yes,
That's
all of these
different.
concepts are connected, a little different because you're not, in a way, you have a constraint on the water fraction, which is similar to variation inequality, but not quite. There's an additional evolution that's going on there. But yes, it's a really good question. Yes.
Okay, so yeah, so the solver you used here is a Newton method, right? Semi-smooth Newton
Yes.
method. So
Semi-smooth Newton method.
yeah. I heard about another solver. It's called augmented Lagrangian. Is it similar? Or is it the same thing or different? Yeah.
So augmented Lagrangian, one could write out a solver depending on how you frame it with the so-called active set method for the semi-smooth model, and keep account of keep track of where your solution goes out of being in one region where the variational equality is satisfied or where you have water fraction or not. And augmented Lagrangian is another way to do it. It all comes down to how general your solver you want to be. There are ways to interpret these together. Yes, but thank you for the question. Yes.
Okay.
Yeah.
So maybe, yeah. maybe the time is up, right?
Yeah, thank you.
We'd like to thank you
Just
again.
is just a small question, if possible.
Mhm.
In the case, I think that it is more realistic to introduce some random parameters in your models. For example, in the case where the temperature suddenly changes. In this case, the random parameters can be very helpful.
Yes, yes, I agree. In fact, I just showed here the slide where you see what the pore scale geometry is. One has to consider, and in fact, we're looking into it very carefully because one has to consider that this geometry is pretty much random. Same as what I mentioned here in getting the upscaled heat conductivities right here. We actually are building probability distributions of the effective coefficients because there's so much nonlinearity, we cannot really resolve it deterministically. So we have to go to building probability distributions. Yes. So we're trying still to find a way to frame it properly rather than just using, we have built a probability distribution function and then we are sampling from it when we're solving at the Darcy scale. So, but yeah, of course, I agree. It's an excellent point. Yeah, thank you.
Thank you for you.
There is no any more question, so we would like to thank you again for accepting our invitation and for your time and sharing with us your valuable expertise. Thank you so much.
Thank you very much. Thank you very much. Thank you for giving me the opportunity to speak. Thank you.